Welcome to the Deep Dive. We're here to unpack complex topics, get you informed fast, and today we're diving into something pretty fascinating, the different ways AI actually understands sequences. Think language, or time series data, even things like genomics.
Yeah, and it's a space where, for years, developers really faced this fundamental trade-off. You had recurrent neural networks, RNNs, things like LSTM, super efficient when the AI is actually generating output that's inference. They use constant, pretty low memory for each step.
Okay, efficient inference sounds good, but what's the catch?
The catch is training them. Because they process information one step after another, sequentially, they're just really slow to train, especially on modern hardware that loves parallel tasks.
Right, and that's where transformers came in. Yeah, they kind of blew the doors open for training massive models like GPT-3 because they could process things in parallel.
Exactly. That parallel self-attention was revolutionary for training.
Yeah.
But like you said, there's a catch there too. That power, it comes with a pretty hefty price tag in terms of memory. It scales quadratically, OVL squared.
Ouch. So longer sequences mean exponentially more memory.
Precisely. Especially for this thing called the KV cache, which basically stores a running memory of everything it's processed. It can become a massive bottleneck really quickly.
Okay, so that sets the stage. Our mission today, then, is to explore, four key architectures, LSTM, RWKV, ARWKV, and Gemma3, and see how each one is trying to tackle this trade-off, pushing the limits without needing infinite memory or training time.
That's the plan. Each takes a really interesting, different approach.
Cool. So let's start at the beginning, more or less. LSTM. Developed way back in '97, which is ancient history in AI terms. It tackled that vanishing gradient problem in RNNs. What exactly made it so groundbreaking?
It was a huge deal because it meant RNNs could finally sort of hold on to information from much further back in a sequence. Before LSTM, they'd just forget things too quickly.
Yeah.
It introduced these really clever ideas. Cell states, like a dedicated memory lane, and gates. Think of gates as like little traffic controllers, deciding what information gets into the memory, what stays, and what gets forgotten.
Okay, so it could theoretically remember things for a long time.
Yeah.
But you said there were still limits.
Yeah, in practice, because training was still sequential, step by step, their effective memory, the context they could actually use well, was often limited to maybe hundreds of tokens, still computationally heavy for really long stuff. But critically, the inference, the generating part, stayed really memory efficient. Scales with the model size, not the sequence length. That's ODAD.
Got it. So LSTM was a big step, but training on super long sequences was still a barrier. Which brings us to RWKV. This one tries to get the best of both worlds, right? Fast training and efficient inference.
That's exactly the ambition. RWKV is fascinating because it has this dual formulation. It means you can train it in parallel, like a transformer, which is fast. But then for inference, it acts like an RNN, super efficient, constant memory per step, still A.
How does it manage that? What's the trick?
The key innovation, and this is crucial, is that RWKV doesn't need a KV cache. All the information from the past is compressed down into a fixed size state vector. It just updates this vector at each step.
No KV cache.
Wow. So theoretically, it could handle infinitely long sequences during inference.
Theoretically, yes. Infinite context. Now, in the real world, if you run inference on sequences much, much longer than what it was trained on, performance might start to degrade a bit. But the potential is huge.
Okay, that sounds incredibly efficient.
Yeah.
But can a model without that big transformer attention mechanism and KV cache still reason and perform as well? This seems like where ARWKV comes in. It's more of a method than a brand new architecture.
Exactly. ARWKV uses a really smart technique called knowledge distillation. You basically take a highly efficient recurrent network, like RWKV, and you teach it using a much larger, more powerful transformer model, something like Quinn 2.5, for example. It's kind of like having a star student learn directly from the absolute master.
So the smaller, efficient model learns the reasoning patterns of the giant one. That's the idea. Through this multi-stage training, ARWKV can achieve expressiveness and reasoning abilities much closer to a big transformer, while still keeping that amazing O1 constant memory inference of RWKV. It makes building these really powerful, efficient RNNs much more practical.
All right, so we've seen RNNs get faster training and transformer-like smarts. What about the other side, making transformers less memory hungry? Enter Gemma3 from Google. They didn't ditch attention, they optimized it, yeah.
Right. Gemma3 tackles that KV cache bloat head on. They use something called hybrid attention. It's a mix. Mostly local attention, focusing on nearby words, but with some global attention layers mixed in. The ratio is about 5 to 1, local to global. Plus, they use grouped query attention, or GQA, which is another way to make the attention mechanism more efficient.
And the result is a much smaller KV cache.
Much smaller. Reports suggest it can be up to 6 times smaller than a standard transformers cache. This lets Gemma3 handle incredibly long contexts, we're talking up to 128,000 tokens, while still maintaining high accuracy. It's a different way to solve the same core problem.
Okay, wow. 6 times smaller is significant.
It really is. And what's truly fascinating, looking across all these, is the convergence we're seeing. RWKV showed RNNs don't have to be slow to train. Gemma3 shows transformers don't have to be absolute memory hogs. They're borrowing ideas from each other.
Yeah, it feels like the lines are blurring between purely sequential and purely parallel approaches. They're learning from each other's strengths. So the big question for you listening is, how might this ongoing convergence, this blending of architectures, actually change how we interact with AI, especially in situations where you need long context, but maybe you don't have massive computing resources? How might it shape the next generation of AI systems you build or use every day? Something to think about.